Yeah, we can see it.
I can see it. Okay, no problem. All right. Let me check. Oops. Okay. Hello, everyone, and welcome to today's talk. Our topic today is looking ahead, how AI transforms mathematics learning. I'd like to spend the next half hour exploring these themes with you. The lecture is divided into four parts: a brief introduction about myself and an era of change, how our world is being transformed by AI and related technologies, and impact on mathematics, what these societal shifts mean for mathematics and how math combines with AI to create new possibilities. And the last one, new directions in math education, how we should rethink math curricula for an AI-rich future. First, let me begin by introducing myself in more depth. My name is Liang, and my journey is a story of change. I studied precision instruments and mechanical engineering at Tsinghua University. After graduating, I joined China's defense industry as an anti-tank missile engineer. On paper, it was a stable, prestigious job. Yet I felt a growing restlessness. I was spending my days running simulations and refining hardware, but something in me longed for a different kind of impact. So I made a decision that surprised my friends and family. I resigned and I joined New Oriental, a major educational company in China. From that moment on, I began a transformation from engineer to educator. At first, I taught English, then gradually shifted to teaching mathematics. In China, I studied with high school English and Gaokao math, and then moved into competitive math, preparing students for contests like EMC, AMY, and for the IB and AP standardized exams. Working with students on these tests exposed me to the strength and weakness of our current system. Eventually, I left China for Canada. I completed the Master of Teaching program at the University of Toronto and earned an Ontario teaching certificate, becoming a fully licensed teacher in Ontario. This arc from engineer to teacher, from China to Canada, reflects my fascination with change. And as I made those personal transitions, I noticed that the world around me and us was changing even faster. Um, Actually, AI is transforming industries and daily life. We are living through an era of transformation driven by artificial intelligence. AI is not just a buzzword, it is reshaping industries, social norms, and even our daily habits. Tools like ChatGPT, DALL-E, and generative search engines have made capabilities that were once the domain of specialists available to everyone. And consider the story of a young innovator named Toby Brown. Uh, at just 16 years old, he built an AI-based assistant called Beam and secured 1 million US dollars investment from Silicon Valley venture capital. Beam is an AI native computer that handle tedious tasks like reading emails, finding files, seeking calendars, and booking meetings. Brown was so committed to his project that he deferred his GCSE exam until 2026. His funding is released in tranches. $400,000 is available now, and 600,000 comes when he raised at his next round. The fact that investors are willing to back a teenager shows how AI is empowering a younger generation. In the past, building a digital assistant would have required deep knowledge of operating systems, file structures, and network protocols. Brown can delegate much of that complexity to AI and instead focus on key questions. Who are my users? What problem am I solving? And what feature actually help them? AI allows him to handle the higher level design and leave the mundane tasks to the machine. Things that seemed impossible for a teenager a decade ago, be building an intelligent system and attracting venture capital, are now within reach. AI isn't just empowering new startups, it's also reshaping the information economy. And The Economist ran a piece titled AI is Killing the Web. Their point isn't just that AI is destroying the internet itself, but that it threatens the traditional web, the network of websites that people visit to find information. For decades, online businesses relied on people using search engines and clicking through their sites. Now, generative tools like ChatGPT and Google's AI summarizes serve information directly in the research results. For example, today I asked Google, what is International AI Olympiad? Then we can directly get the answer by the AI. The International Olympiad is in artificial intelligence is an annual global competition for high school students to test and foster their knowledge and skills in artificial intelligence. And you can see there are five resources at the corner, right up corner. But a research article notes that when you search on Google today, you often see this AI generated summary of the answer before any links. According to some estimates, fewer than 1% of users bother to click through the original resources after reading these AI summaries. Actually, that's a big problem for companies like Google, which depend on advertising revenue from those websites. Yet, Google still rolled out the feature because if it doesn't, someone else like OpenAI will do this. So, this AI-driven race shows that companies must be willing to disrupt themselves or risk being overtaken. So we are used to thinking of progress as something linear, faster computers, bigger databases, more sophisticated algorithms, but AI creates a discontinuity. When a machine can write code, summarize articles, and solve math problems, what does that mean for human skill sets? It means we need to shift our focus from routine tasks to uniquely human abilities, such as understanding context, exercising judgment, and nurturing creativity. So, for the impact on mathematics, now that we understand the broader context, let's examine how these changes affect mathematics specifically. I see three major shifts. The first, the diminishing value of traditional standardized exams. Second, a shift from closed problem to open-ended problems. Third, a move from generalist to specialist mathematics. For decades, students have devoted to countless hours to standardize the math tests, the Gaokao, SAT, IB, and AP exams, not to mention competitions like AMC and AME. These tests typically assess your ability to solve well-defined problems quickly and accurately. In the past, speed itself was valued. Many parents in East Asia, for example, enrolled their children in abacus mental arithmetic classes like 珠心算. It was impressive to see a child rattle off multiplications in seconds. Um, Maybe in 20 years ago, this was considered the height of mathematical skill. But once calculators become ubiquitous, the advantage of raw calculation speed eroded. In many standardized exams today, you are allowed and sometimes required to use a calculator. Take the AP calculus exams. The College Board explicitly allows and in one section requires a graphing calculator. Their policy notes that various AP exams permit calculators and that you may bring a calculator into the exam. The policy lists brands and models of acceptable calculators and stresses that certain sections of AP calculus demand a graphing calculator. This means exam designers know that manual computation isn't the primary skill being tested. Similarly, the IB program provides an extensive calculators guidance for examinations. The document notes that calculators are not allowed in paper one, but for paper two and three of both AI and AA, uh, both high, standard level and high level. And students must bring a graphic display calculator. The required functionalities include plotting graphs, solving equations, like adding and multiplying matrix, finding numerical derivatives and definite integrals, and even performing matrix operations like finding determinants and like eigenvalues. In other words, calculators are not just permitted, they are expected to handle complex tasks. When exam boards allow calculators with matrix operations and numerical integration, the value of hand computing integrals or solving systems by substitution diminishes. I've seen math PhDs struggle through pages of complex linear algebra to solve an IB problem, only to find that the official solution uses the matrix function on a TI-84 calculator and gets straight to the answer. So, for the implications for learning, the key questions becomes what are we trying to assess? If a computer can differentiate functions in microseconds, why should we spend months training students to do it by hand? I'm not saying we should abandon calculus. Understanding limits, derivatives, and integrals are essential for many sciences, but we need to recognize that procedural fluency is less valuable than conceptual understanding. Instead of asking what is the integral of sine x, we might ask how does changing the amplitude of sine x affect the area under the curve? Or why does the derivative of sine x related to cosine x? Assessments should focus on reasoning, interpretation, and communication. The standardized test of the future might look very different. They could involve explaining your thinking or critiquing a model rather than plugging numbers into a formula. Okay. Um, the, the second major shift is from closed problems to open-ended problems. In traditional math education, most questions have a single correct answer. You compute a number or solve a variable. Even competitions like AMC, which are very challenging, eventually have one solution. But in an era when AI can produce the answer to a calculus problem almost instantly, unique answers lose their educational value. The world our students will enter is full of ill-defined problems, optimizing supply chains, maybe, predicting climate change, designing fair algorithms. For example, here is a question like this. A delivery company wants to use autonomous drones to deliver packages in the city. The city is a grid of intersections. Some intersections are blocked by building or no-fly zones. Each drone has a limited battery. Design a mathematical strategy or algorithm to decide which route the drones should take to minimize total delivery time while ensuring all packages are delivered safely. Notice that there are no equations handed to you. You must define the variables yourselves. And what are the coordinates of the package? Which intersections are blocked? How far can each drone travel? Then you must decide how to represent the problem, perhaps as a maybe weighted graph, where nodes are deliver points and edges represent travel distance. So that's basically graph theory. You must choose an algorithm to find routes, perhaps like Dijkstra algorithm for shortest passes or heuristic for the traveling salesman problem, or a constraint satisfaction approach to consider battery life and no-fly zones. There is no single right answer. Different strategies will have different trade-offs. The educational values lies in modeling, reasoning, and justifying your choices. By engaging with open problems, students learn to translate real-world scenarios into mathematical language. They also learn that mathematics is not just about producing numbers. It is about making assumptions explicit, testing those assumptions, and communicating the results. These are skills that AI cannot easily replicate. AI can crunch numbers and propose solutions, but humans must decide whether a model can make sense, whether the assumptions are ethical, and whether the results are meaningful. In a world with AI, the competitive advantage lies in posing the right question and evaluating the answers critically. The third shift is a move from generalist to specialist mathematics. Traditionally, math education aims to create all-rounders. Students study algebra, geometry, trigonometry, calculus, and a bit of statistics. This broad foundation is valuable for general problem solving. However, as AI automate more routine tasks, we need to consider where human expertise is still essential. Modern AI models rely heavily on linear algebra, statistics, probability, and optimization. Neural networks are essentially arrays of matrices and vectors. Training a neural network involves calculating gradients and adjusting weights using gradient descent and optimization algorithm. And understanding these processes requires knowledge of vectors, matrix multiplication, eigenvalues, numerical derivatives and integrals, probability and statistic underpin machine learning models like logistic regression, random forest, and Bayesian networks. Even simple decisions like which ad should I show this user relies on probabilistic reasoning. Meanwhile, topics like Euclidean geometry, for example, constructing proofs, drawing auxiliary lines to show two triangles are congruent, have less direct relevance for AI and many applied fields. Though they remain important for pure mathematics, that doesn't mean geometry is useless, but in an AI-driven era, it may deserve less emphasis for most students. The time saved can be spent on linear algebra and algorithm thinking. So that's why we should restructuring the timeline of math education. To accommodate this specialization, we need to reshape the entire timeline of math education. Traditionally, we divide math into elementary, middle, and high school. In elementary school, children learn basic arithmetic like addition, subtraction, multiplication, division, the shapes, measurement, and patterns. In middle school, they tackle integers, equations, coordinate geometry, and basic statistics. In high school, they study algebra, calculus, and probability. This progression served the industrial age, where general numeracy was the goal. But to prepare students for an AI-rich future, we must weave new topics throughout this journey. For example, in elementary school should be about more than multiplication tables. Students can start learning what data is, how to collect it, record it, and represent it with simple charts. They can learn the concept of an algorithm by following step-by-step instructions or even writing a basic recipe in pseudocode. They should experience solving problems collaboratively and see how math connects to real life. In middle school, we should introduce data representation like tables, histograms, scatter plots, and probability models, simple random events, simulations with, for example, dice or coins. Students can experiment with vectors on the plane and perhaps manipulate small matrices as errors of numbers. They should also see how algorithms apply to math, such as using a sorting algorithm to organize data or exploring search algorithm in games. High school should delve into linear algebra, numerical methods, optimization, discrete mathematics, and data analysis projects. The IB calculator guidelines offer insight into what high school students can be handled. For IB Mathematics Paper 2 and Paper 3, the required calculator must be able to plot graphs, solve equations, both real and complex, add and multiply matrix, find numerical derivatives and definite integrals, and perform matrix operations like finding determinants and eigenvalues. That means high schoolers are already expected to use tools that handle matrix algebra and numerical calculus. Our curricula should therefore teach the underlying concepts so students understand what the calculator is doing. They should also learn optimization, like maximizing or minimizing functions, which is at the heart of machine learning, and discrete mathematics like graphs, combinatorics, logic, and these underpins algorithm and cryptography. By introducing these topics earlier and in a scaffolded way, we demystify advanced mathematics and make it accessible. The goal is not to produce a generation of machine learning engineers, but to build data literacy and algorithm thinking for all students. To conclude, let me recap the key points. First, my own career has been a journey of change from engineering to teaching, from China to Canada. This personal story mirrors the rapid change we see in the world around us. We live in an era of change driven by AI. Teenagers like Toby Brown can build AI-powered products and attract serious fundings. Search engines are evolving into answer engines, threatening traditional web business models. These changes have profound impacts on mathematics. The value of standardized exams that emphasizes speed and accuracy is diminishing. Calculators are not just followed, but required. We need to shift from closed single answer problems to open-ended real-world problems that required modeling and judgment. We must move from a generalist approach to a specialized one that foregrounds linear algebra, statistics, optimization, and algorithms. And last but not least, math education must adapt. We should introduce data and algorithm thinking early, weave in probability and basic linear algebra by middle school, and teach high school students the tools that underpin AI, such as matrix and numerical. AI can support personalized learning, but human teachers remain indispensable. We must also address ethics and equity, ensuring that all students have access to AI tools and are taught to use them responsibly. So, looking ahead, my hope is that we will embrace these change with curiosity and creativity. Education should empower students not just to use AI, but to shape it, to ask better questions, design fairer systems, and build a more just and innovative world. Okay, thank you for listening, and I look forward to your questions.
Okay. Thanks for Liang sharing. Maybe we, due to the time limit, maybe we have just one question.
Mhm.
I see in the chat box. What kind of math scales